Hi everyone, and thank you for watching this presentation about delegate covariance and parameter passing in D. The content of this presentation is available at this GitHub address or on the dconf.org website. My name is Mathias Lang. You'll find me under the alias Geode24 on GitHub. I discovered D some 8 years ago, started contributing, joined Sociomantic, and I am currently CTO in a company called BPF Korea, or BPFK for short. BPFK is a blockchain company. To be precise, we are working on something called the decentralized ledger. If you have no idea what that means, for the purpose of today's presentation, you just have to know it's a peer-to-peer server application. Most of said server application is written in D, augmented by a third-party C++ library. We currently have 9 people working on the server itself. Out of those, 2 people have previous experience with the language, so including myself, and previous experience at Sociomantic, to be precise. Most of the work we do is open source, and you can find it in the GitHub organization BPF Korea. Our main project, the server, is named Agora, and if you're curious about the project itself, I also included a link to our website. So, why did we go with D? Well, it wasn't out of personal preference, really. First, we needed a modern language, something performant that gave us complete freedom over every aspect of the project. Hence, a strongly typed system programming language. As mentioned, we also needed to integrate with a modern C++ code base. When we first evaluated our options, it was C++ 11. If it since upgraded to C++ 17 nowadays, and so for to integrate with modern C++, short of using C++ itself, D is hands down the best contender in that area. And last but not least, the ability that D provides us to quickly prototype something, and yet being able to turn such a prototype into something that can be deployed in production fairly quickly is really great. Um, I believe that this ability, we owe it to the combination of first sensible permissive defaults, things like system by default, mutability by default allows us to prototype quickly, but also the lack of false positive diagnostic from the compiler that you would usually find in C++ is something that is a real breath of air. Um, of course, we also have some pain points. Debugging made it to the top of that list very easily. Debugging isn't a great experience compared to other languages, and this is made worse for us by the fact that our developer machines are all on Mac OS X. Additionally, Dub is giving us a hard time. It has gotten so bad. I assigned one of the developers to fix a few bugs, as the workarounds are becoming increasingly time-consuming. But thanks to Dub being open source, and most of those bugs are currently being fixed, and I'm pretty confident that I can remove it from this list in the future. On the language front, we've been beaten a few times too. In particular, we had memory corruption issues because DMD was moving some structs. Two structs turn out to be or to contain extend C++ struct with internal pointer to themselves or other structs. Well, you might know that internal pointers in D is a big no-no. The problem is that we're interfacing with C++, and in C++ it's not uncommon to have internal pointer. Um, and we tried things like disabling post-split, but sometimes DMD didn't care. Luckily, thanks to the awesome work of Martin Kinkelin on LDC, LDC got a few improvements to its return value optimization around the release 1.20, I believe, which solved most of our problems. So we just dropped DMD compatibility, and we're happy LDC users since 6 to 8 months, I'd say. And um, last but not least are attributes. So at Sociomantic, we never used attributes, even after the D2 transition, because of how painful it is to write library code for them. Supporting any combination of attributes is not something trivial. One would naturally go for templates as they carry and infer their attributes, but templates also cannot always be used. If you use like classes on inheritance, templates are a no-go, and if you use delegate as parameter, you need to template the function, but sometimes you just can't. So there's nothing to solve this issue. Um, so it's an issue we had in our own code base. It's an issue we had in libraries we were using because we're using Ocean, which was Sociomantic standard library. We're using VibeD, which uses Delegate quite a bit. So that problem with attribute was one key language problem that we had to deal with, and that I believe we now have a fix for it. So what's the fix? So essentially, the way we use delegate is that we use them for composition quite a bit. We have what you could call delegate-driven code. It's um, it's usually for utilities that needs to deal with a wide variety of types, allows for some user customization, are easy to compose, and mostly we use it to defer some kind of aggregation. The most common case is obviously allocation. It allows us to defer allocation logic to the caller. So for some example, I'll be presenting three examples here. We have hashing, we have our custom serializer, and we have string formatting, the pretty printer, which comes from Ocean. So let's start with hashing. Such a delegate-driven approach usually has three components. In our case at least. First, we have a method called something full, in this case hash full. It's the user-friendly entry point, taking a record as a parameter and returning the result, while something part, hash part in this example, takes a record and a delegate. The part function actually contains the implementation, and hash full just provides a useful default delegate. Finally, at the bottom, you can see the alias to the delegate type. In this case, the delegate just accepts binary data. We never keep a reference to this data. We deep copy it as needed. So in this case, just means const scope. You can see at the bottom of the slide, there's a link. So if you downloaded the slide, you can follow this link and see the actual code, which is slightly more complicated than what I could put on the slide. And all the following example will have such a link. Um, and as you can see in hashpart, the first thing we do is to check if the user provided hook exists and call it if possible. Otherwise, the rest of the code handles the default behavior for most types. If it's a composite type, for example, such as an array or struct, we iterate on the elements or members, and for basic type, we pass a platform independent binary representation to the delegate. Fairly straightforward. So this is what a record in our system would look like. Here our input struct implements compute hash for two reasons. First, to ignore the sig field as a signature in the cryptographic sense, a signature is generated from the hash, so it cannot be part of the hash, obviously. And second, we might want to handle certain kind of data differently, as done with the commitment field in this case. And in our second example, there's a binary serializer, much of the same thing here as a full and part method with an associated delegate. And obviously, we have implemented deserialization using the same pattern, although our deserialized part returns a value just to allow an RVO to take place. And here our serialized DG takes binary data, while deserialized DG takes a size and return an ephemeral buffer of that size. So once again, I'm sure many of you have been implemented a serializer, pretty straightforward. And finally, we have Ocean's formatter. Here you can see the three most common overload, the Phobos-like format approach, which takes a format string parameter, returns a newly allocated string. S format, which is essentially format part, if you will, accepts format argument and delegate, and that's where most of the implementation is. And finally, SN format. And this one just accepts a pre-allocated buffer and will write up to that buffer size. As we can see, everything is built around the delegate overload. Here we have format, and while SN format didn't quite fit on the slide because of the length tracking code, it is simply doing bookkeeping in our position in our buffer, so it's around 25 lines as well. Here the delegate is pretty simple. It's just happening to a buffer, but with a more complex pipeline, our delegates could do pretty much anything. For string formatting, we might just be appending to a file object, as in the C file object under the hood. We could be relying on its buffer instead of GC allocating our buffer. For serialization, the delegate could be reading from or writing directly to a socket, reducing the number of intermediary buffer. And for hashing, we can just replace the hashing algorithm. In our case, we use Blake2B, but you could have, I don't know, a dual SHA-256, and that would be just a two-line change in the call. So that really allow us to be very flexible in what we do and to try out different approaches very quickly. And finally, our delegate could just wrap another delegate. It could be to filter data, as in this example, could be to provide extra buffering, and or just adding extra app level logging for the purpose of debugging. And obviously, that can be done at any level. In this example, the record knows approximately what amount of data it will output, so it provides a more optimized buffer in between. There's just one little problem. If you were to write that code, well, computer would say no. The compiler would complain about mismatched attribute. The problem is we suddenly want to throw, but our delegate is marked as no throw. Why is it marked as no throw? Because otherwise our little hashing utility wouldn't be callable from no throw code. And we, in fact, have currently no reason to throw. But when writing library code, that reasoning doesn't quite fly. You have to assume that someone at some point will have a very good reason to throw from here, unfortunately. You might also note that pure is commented out. It's because we use a C function which does some very impure things. If we were to change the implementation though and have a pure hash function, we still couldn't use it from pure code. That's a shame. What we would really like to be able to do is to specify that our function's attributes are dependent on the delegates attribute. While thinking about this problem, I realized that it's something we actually already solved, but for constant immutable. That's exactly what inout does. If you need a refresher about inout, I highly recommend Stephen's presentation from one of the previous DConf. So introducing a new keyword in our case was out of the question, and especially not one per attribute. So we couldn't do exactly what inout does by introducing a new keyword. We needed a slightly different solution. So my approach was instead to extend the grammar to allow an argument list to be present after those attributes. Those argument-dependent attributes, or ADA as I call them, will only play a role in two cases. First, the compiler will not enforce that a delegate has a certain attribute if it can find such a dependence. Second, at the call site of toString, the caller knows what attributes are on the delegate it passes, and as a result, it knows what attributes toString actually has. So ADAs essentially extend the prototype of a function. ADA don't need to apply to all attributes. If we really want to enforce usage of safe in our code base, we just put the regular attributes on the function and the delegate, and things work just like they did before. Just like inout, ADAs allow to compute the product of attributes. Here, if either sync1 or sync2 is not safe, toString won't be safe either. And finally, they are composable. Your function with ADA can just forward its delegate parameter to another function. And note that ADA are in between unattributed and attributed. An attributed function, so a function which have add safe on it, can be passed to a function which accepts an ADA delegate. And if you have a unattributed function or function with add system on it, you can pass it to the same function. But if you get a delegate parameter, an ADA delegate parameter, you cannot pass it as an attributed delegate because obviously it is not known from within your function. It will be known from the call site of your function. So the compiler will prevent you from doing this. So just like const is a middle ground between mutable and immutable, ADA is a middle ground for delegate attribute. Additionally, this would solve some long-standing problems in the language. Op apply, for example. At the moment, if you declare an op apply for a record, for a struct, a class, whatever, you have to pick the delegate attributes and stick with it, or provide a gazillion overloads. You could make op apply templated, but then the compiler will not be able to do type inference on the for each. You'll need to provide types explicitly when you do your for each iteration, which is not very convenient. And another one is also that it can mitigate some issues with objects. There has been a proposal to make something called proto-object, but as far as I know, nothing has materialized yet. But using ADA, we could make toString accept a sync delegate, or toHash accept a sync delegate, and that would allow to call them in safe or pure context. It's also a backward compatible change. All code that used to work before the introduction of ADA will continue to work after it has been introduced. And there's place in the runtime that could benefit from it. For example, Tróbol toString. Tróbol toString uses the sync approach, but as problems I mentioned, it doesn't work with attributes. So Regarding the timeline, I've been slowly working on a proof of concept for a few weeks or a few months now, and I will use that as a basis to write a proper DAP, so to go to the proper tunnel. But my proof of concept was to make sure that things would actually work, and so far they did work exactly as expected. So I'll write a proper DAP, submit it, and hopefully within the first quarter of 2021, that should be ready. All right, so now that we covered delegate covariance, it's time for parameter passing. Um, in particular, I'll be explaining what is the preview in Switch, how it came to be, and why you will enjoy it too. So, if you remember the examples I used before, hashing serialization and string formatting, you might have noticed that the record was annotated with in, and unfortunately that wasn't the real code. The prototype is actually closer to what you can see now. Our record is scope const autoref. Scope because it doesn't escape, and const because we don't modify it, and finally autoref because we don't really care if we get a reference or not. If we can avoid a redundant copy, as a record can be quite large, we'd like to do so. So what is preview in exactly? It's a new preview switch available since the latest release of DMD 294 and the latest release of LDC 124 that completely changes the meaning of in. The previous meaning of in was just const. Then in 293, a switch was introduced to make it mean const scope, and since 294, it has a different meaning. So if you want to use this preview switch, it's as simple as throwing dash preview equal in to DMD or LDC. And I recommend to use it in combination with the DIP 1000 preview. Otherwise, scope violations won't always be diagnosed. Scope violation relies on DIP 1000. So why this change? Well, many of our, if not most of our parameters are const scope. And whenever we can, we add autoref to the mix. But autoref requires that you use a template. Once again, if you use OOP, that's not going to work well. And in some cases, like for a delegate argument, you just cannot use it because you would have to template the delegate type, and the delegate type parameter need to be the template argument, which means the template argument deduction will not work. But the auto part is needed in D because unlike in C++, we don't bind R values to const reference, which is the same thing to do, but does make things or does make our life harder. So, for example, you cannot provide the return value of a function to as a parameter, as a ref parameter. You need to assign it to a variable and then pass this variable instead of having the call in line. But if your parameter is also const and scope, that doesn't make much sense from the programmer's point of view. So how does it work? Earlier I mentioned that it completely changes the meaning of in, and that is the way you should think about it, not in the framework of the previous in, but it as something completely new. So first, think about your parameter as being passed by ref. It might be passed by value if the compiler thinks it's small enough, but you should not rely on it being passed either by ref or by value. If you pass an error value, it will be constructed at the call site and destroyed when the function returns. If your type has side effect, for example, a destructor or copy constructor, it will never be passed by value, no matter how smart the type is, because you don't want to side effect with trigger. And that is one of the main reasons we really wanted this. It makes interacting with C++ much easier, because then we can start to pass smart pointer as in parameter to decode. And finally, you have to be careful of parameter aliasing. That's something that was brought up a lot on the forums. Since you shouldn't rely on the way the parameter is passed, if you alias a parameter to an in argument and another mutable argument, and you mutate the other mutable argument, you might have different behavior. Your function might exhibit different behavior. In practice, I've never actually even seen someone do that. I reviewed all the libraries that are on BuildKit, which are the most popular library on the dub registry, and none of them showed anything remotely similar to this. Most of them could exhibit the pattern of using const scope autoref and could benefit from it in. And as shown earlier, well, all the examples shown earlier were, I think, a good showcase of what in allows you to do. Instead of having const scope autoref for a parameter that you're just gonna consume and derive something from, be it a string representation, a hash, or binary serialization, you can just use it. And so the core idea here is that in is here to specify what the parameter is semantically, instead of saying how it is passed. An in parameter is input only, so it affects the result of the function, but it is not affected itself. Output parameters, on the other hand, should not affect the result of the function, but will be affected by the function. That's why an output parameter is notified when you enter a function. And lastly, ref is an input and output parameter. It affects the function, it affects the result of the function, but it is also affected by it. It's mutated by it. In fact, back in the days, ref was actually called inout for this reason. So I did mention that the feature is still in preview mode, and that could sound scary, but actually quite a few projects have been adapted to support it. Obviously, Phobos 5D, Mir, and many other that come from the list of package we test DMD, runtime, and Phobos with. So the BuildKit packages. Additionally, the feature has a built-in safeguard. It encodes whether or not a reference is used in the mangling. So you shouldn't be worried about mismatch, because if you ever have a mismatch for whatever reason, the linker will not link your functions. So there's no risk of runtime corruption. And finally, the only thing that is actually blocking us from using it is debug. And we have one of our dev working on it, so I expect this bug to be fixed fairly soon. And hopefully, the next release of Dub will have it fixed, and everyone will be able to enjoy preview in. So from 2.95. And that's it. Thank you for tuning in. And if you have any more questions, feel free to reach out by email, on the chat, or on GitHub.